Today, we're going to finish our titration unit by focusing on how we can use what we've learned about standardization, primary standards, and the data associated with a titration experiment to establish the concentration of a biomedically relevant analyte, calcium ion, in a urine sample. Now, calcium ion may seem like a relatively mundane analyte and not particularly remarkable in any way. However, calcium is one of the most important analytes in terms of diagnostics in a medical context, particularly when you're looking at calcium concentration in urine. The level of calcium, or the calcium concentration in urine, is particularly important for understanding whether a patient may be at risk or suffering from kidney stone formation, parathyroid dysfunction, kidney dysfunction, or osteoporosis and calcium loss from bones. And so there are a variety of medical diagnoses that rely on accurately establishing the concentration of calcium in urine. Most of these conditions can be at least relatively painful, and some of them may be life-threatening or significantly impede a patient's quality of life. We're going to focus in, give you just a few details on kidney stones. Kidney stones are relatively sharp and jagged crystals of calcium oxalate. So that's the same precipitate we showed you how to produce in a gravimetric analysis the other week. But in this case, the calcium oxalate crystals form in your kidneys. There are a number of environmental and genetic components to the development of kidney stones. But in general, Americans suffering from kidney stones is on the rise. And this turns out to be something that's very important to diagnose quickly and treat quickly. Diets that are particularly high in calcium or high in oxalate put you at slightly higher risk for kidney stone formation. For those of you who have had a family member or someone you know suffer from kidney stones, you know that this can be an extremely painful condition, where the formation of these calcium oxalate crystals in your kidneys can lead to a variety of pretty debilitating symptoms, from extreme fatigue and fever to acute abdominal pain and pain while urinating. So kidney stones can be extremely painful. 1 out of every 11 adult Americans suffering from kidney stone formation at some point. That makes kidney stone formation more common than stroke, more common than severe cardiovascular disease, and makes it one of the most painful and one of the most common medical afflictions in the United States today. Fortunately, kidney stone formation is rarely life-threatening unless it goes untreated for a very long time. But a quick kidney stone diagnosis is important to mitigate a patient's pain level and ensure that they can pass the stone quickly, which, considering how painful kidney stones can be, is something that the patient really appreciates. Now, prior to the early 1970s, if you wanted to diagnose a patient with kidney stones, one of the key diagnostics would be that you have to establish the concentration of calcium in their urine stream, and or identify the presence of calcium oxalate, small calcium oxalate crystals in their urine stream. And classically, before modern instrumentation became available, one of the fundamental ways to do this was to employ a titration for calcium, which actually consisted of multiple steps. So the way the titration would work is it begins with a gravimetric analysis performed on the urine sample, and the precipitate that you make in the gravimetric analysis is then digested with heat and acid to redissolve the calcium and the oxalate, which is then titrated with permanganate in a redox titration. So this is essentially a 3-step chemical reaction to determine the calcium concentration level. This is the classical method for analyzing for calcium in urine. The calcium in the original urine sample is precipitated through a slow precipitation with oxalate to form calcium oxalate solid, CaC2O4. This calcium oxalate solid is dried, isolated, and then digested in heated acid to redissolve the calcium and to make 1 mole of oxalic acid, the conjugate acid of oxalate, for every mole of calcium that was in the precipitate. The oxalic acid is then reacted with permanganate, which is a good oxidizing agent, in the presence of acid to produce manganese 2+ ion, 8 moles of water, and 10 moles of CO2. The stoichiometry of this reaction between oxalic acid and permanganate is 5:2. And the key aspect here, which makes the titration very feasible, is that you don't actually need a separate indicator because the permanganate is highly colored. It's a very bright purple. And so initially the titration starts out clear colorless because every mole of permanganate that you titrate into the oxalic acid solution reacts and you form a clear colorless solution because manganese 2 ion has no color. Once you get a slight excess of permanganate, the solution stays a very faint purple, and that's the end point of the titration. Because at that point, all the oxalic acid is used up, and there is nothing left to consume that permanganate. So the end point of the titration is a faint purple color that just persists in solution for a couple of minutes, and then you know you've reached your end point. In order to do this titration, you need to establish the concentration of your permanganate solution. You need to standardize the solution. So remember from last week, standardization is a procedure where you establish the concentration of your titrant by titrating it against a primary standard. The fundamental idea here is potassium permanganate cannot be purchased as an analytically certified primary standard. And so when you prepare a permanganate solution, you have to establish its exact concentration by titrating it against a known primary standard. Remember, a primary standard is a chemical compound that you can buy better than 99.5% pure, is stable under typical storage conditions, and is stable under heating. So the purpose of the standardization procedure is to take your titrant, react it against a primary standard, and establish the concentration of your titrant in a separate titration before your main titration assay. And in this case, the primary standard that you can use is sodium oxalate, which is the same counter ion that you have in your calcium oxalate precipitate. If you acidify sodium oxalate, you can form oxalic acid, and you can purchase sodium oxalate as a primary standard with a known purity and guaranteed stability under storage. So in this titration, your first step would be to determine the concentration of your permanganate by doing the same titration against a known concentration of sodium oxalate. And then you would have your titrant concentration. Once you knew the exact concentration of the permanganate in your titrant solution, you can actually run your assay and establish the concentration of calcium ion in the urine. So in just a second here, I'm going to turn you loose with a problem where we look at some data related to the standardization of permanganate, and we use that data to establish the concentration of calcium in a patient's urine sample. This is the titration reaction that we're going to be working from. It's written in a net ionic equation form here. You'll see it again, but it's good to make a note of it now. 5 moles of oxalic acid reacts with 2 moles of permanganate in the presence of 6 moles of protons, make 2 moles of manganese 2 ion, 8 moles of water, and 10 moles of CO2. We are going to have 2 goals in our titration problem. We need to use data from a standardization experiment to determine our concentration of permanganate in our titrant, and then from there we're going to use that data to establish the concentration of calcium in the patient's urine. Remember, when working a titration problem, our general strategy is always going to be the same. We're going to take the endpoint volume of the titrant, use the titrant concentration and the reaction stoichiometry to establish the moles of the analyte. Then, using the volume of the unknown, we divide the moles of the analyte by the volume of the original unknown to get the original analyte concentration, which will be the calcium concentration in this case. In the initial step, we're going to flip these early moving parts on their head a little bit because we will know the concentration of the oxalic acid in the standardization experiment, and we will use that to establish the concentration of the titrant. We'll kick that off in our next module, so I'll meet you there in just a minute. Let me know if you have any questions.